Hi guys, welcome to Module 7. This week we're talking about quadratic transformations. So for the next 2 weeks we'll be determining the effects on the graph for the parent function f of x equals x squared, which is this quadratic that we're used to, is transformed using f of x equals a times x minus h squared plus k. I know that looks complicated and tricky, but for this week, we're only going to talk about a. And with this transformation, it's talking about changing the width of our quadratic. So it might get more narrow depending on the value of a, or it might get more wide, or it might be a reflection over the x-axis. That's what we're going to talk about today. Before we get started, I'm going to just make a quick table of the parent function values of x squared. So what that means, I'm going to go from -3 to +3. Just so I have some reference points to work off of whenever I get to the notes. So -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Of course, that's why I get that U-shaped curve, because those y values start to repeat there. So let's first talk about this transformation called a vertical stretch. A vertical stretch happens when the absolute value of a is greater than 1. Remember what absolute value means. Absolute value means always think of it in the positive form. Okay, as a increases, the graph will become more narrow than the parent function. So the parent function is, let me change the color here. The parent function is, let's do rainbow. This rainbow graph here, let me go there. This is the parent function. Okay. I am actually wrong. That is not the parent function. The parent function is this dashed line. Okay. So the parent function, if you look up here, it matches that parent function. So what happens when you have a vertical stretch is your parent function gets a little bit more narrow depending on the value of a. But this one right here is actually that transformed function. Because the value of a has increased, the graph has gotten more narrow. Think of it as stretching a rubber band. If I keep stretching and stretching that rubber band, think about how thin and narrow that rubber band would get over time. That's basically what's happening to this graph here. So I'm going to go through and actually highlight my next parent function here. So if I notice, there's the parent function, but if I look at this graph and I think, hey, what happened to this? Going from this rainbow function to this second function that's written here, what happened was a vertical compression. A compression means that the value of a, the absolute value of the value of a, so the positive value of a, is between 0 and 1. So think of some numbers between 0 and 1, like 1/2, 1/3, 2/3, 3/5, those type of numbers. Fractions where the number on top is smaller, or we could even say decimals such as 0.5, 0.25, etc. You'll usually see fractions though. Those types of numbers, when they are in front of x squared, for instance, if I had 1/2 x squared, that would make my graph much more wide as such. And then finally, a vertical reflection. What happens on this graph is the value of a is negative. Let's find that parent function. Here's my rainbow parent function. And what happens on a vertical reflection is the value of a is negative. See, less than 0, what numbers are less than 0? Well, those are my negative numbers. So if I had a graph that was like y equals negative x squared, negative x squared, even though we don't see a number here, I could say negative 1x squared if I really wanted to. And if I had something like that, then that would cause a reflection over the x-axis. So in green are the transformations. In rainbow, that's just the parent functions. All right, I'm going to keep that theme up as we work through a couple of examples here. So what we are to do is to sketch the following transformation given the parent function and identify the transformation. So first thing I'm going to do when I'm identifying the transformation, I'm looking at this value in front of x squared. Notice that the value is 2. And since that's the case, let's go up here and see. A vertical stretch is when a, the absolute value of a is greater than 1. Is 2 greater than 1? I sure believe it is. So this would be a vertical stretch. By 2. We would typically say a scale factor of 2, but for the sake of time and space on this paper, I will just write that vertical stretch by 2. So my parent function, I'm going to again go ahead and just use my rainbow color to make it stand out a little bit more. And I'll do the same over here. And what I'm going to do is I'm going to go ahead and stretch this graph. How I'm going to do it, I'm going to do it basically mentally in my mind. If you were in class, what you would do is probably use your calculator. But I'm going to just take that table that we had a little bit earlier up at the top. You can write it here if you like. And because that value is 2, what I'm going to do is basically double each of these y values. So that's how I'm going to create this vertical stretch. But I'm going to do it rather quickly and in my mind, because in the class we would have just used our calculator. So instead of having the point 0, 0, I'm going to have 0, 0. Instead of 0, 1, I'm going to double this y value of 1. I'm going to have 1, 2. Instead of having 2, 4, I'm going to double this value of 4 to 2, 8. And I'm going to do the same thing going in the opposite direction. Instead of negative 1, 1, I'm going to have negative 1, 2. And instead of negative 2, 4, I'm going to have negative 2, 8. There's my transformation. That would be a vertical stretch, you can notice, because it's more narrow. Looking at number 2 here, the transformation, it says y equals 1/2 x squared. We're mainly looking at that number in front of x squared. So because that number is between 0 and 1, look back at your notes. A number between 0 and 1 is a vertical compression. So I'm going to put vertical compression by 1/2. Vertical compression by 1/2. All right. So just how on number 1, how I doubled all the y values, what I'm going to do for the vertical compression is I'm going to take half of each of the y values. I'm going to start at 0, 0, 0. That doesn't change. But 1, 1. My x value is 1. My y value, instead of being 1, I'm going to do half of that, so 1/2. Instead of 2, 4, I'm going to take half of 4, is 2, 2. Instead of 3, 9, I'm going to have 3, half of 9 is 4.5. So it'll be like that. And I'm just doing a rough estimate. And if I wanted, I could probably figure out some more points. But if I notice here, this graph is wider than the original graph because it is a vertical compression. Moving forward, I'm going to go ahead and make my parent function stand out a little bit more using my rainbow color. I guess it's more of a galaxy or outer space type of thing. But you get the idea. Those are my parent functions. And again, I noticed on number 3 that it says negative x squared. So I'm going to look at my reference chart and see if it's a vertical reflection, that's when a is less than 0. So -1 is less than 0. So therefore, this is a vertical reflection. All right. This one's not too bad to do. Again, I could look at these points, and on my y side, I am multiplying them all by -1. So basically all the values would be upside down. So 0, 0, 1, -1, 2, -4, 3, -9, and then I'm going on the other side, -9. So here's what my reflection would look like. And I missed. Let's try it again. There we go. All right, and this final problem is our challenge problem. Why is it a challenge? Because if you look at it, you'll notice two things. It has a negative, and it has a number that's, if I took the absolute value of it, it would be between 0 and 1, which would be a vertical compression. So this actually has two transformations. The first one is a reflection because of the negative. And the second one is a vertical compression. By 1/3. All right, so in order to do one like this, typically you guys would use your calculator. Since we don't have that option today, I'm going to take it in pieces and I'm going to make this work. You could just take a moment and multiply all these y values by -1/3, but I'm going to take it in two parts. I'm going to do the reflection first and then the 1/3. So for the reflection, we already know how to do that. We did it on the other side. 9. This isn't going to be my final graph, so I'm just using it as a placeholder. This would be where my reflection would go. But that vertical compression by 1/3, it's going to make my graph much wider. So let's go ahead and see how that works. So I'm going to take each of these points and make them 1/3 their size. So this was -1, so I'll make it -1/3. This one was -4, so -4/3. What I'm doing is I'm basically dividing these y values by 3. That's about 1 1/3. And then -9 divided by 3 is just -3. And I'm going to do the same thing on the opposite side. If you notice, this is a reflection, so it makes it a little bit easier to do. And I'm going to just kind of estimate the width of that graph. And if you notice, it is wider than that orange graph would have been if it was only one transformation. All right, you guys, that's it for this week. If you have any questions, make sure to contact your teacher and attend your online Google Meets.